Alright, I'm going to do a series of AP Physics 1 review. This is specifically for the 2020 exam. This is going to be video 1, and I'm going to put it into sections so that you can follow it a little bit easier. The exam will be on Thursday, May 14th at 1 p.m. Pacific Standard Time. Now, I think that is the first testing, and I think they're also offering another testing. So this one will cover either one of them, but if you're going to take the one on May 14th, this one will work out for that. So if we take a look at what sections they're going to test, they're only going to do 7 of the units. So here are the units that I'm going to cover first, and I'm going to try to chunk them out. In other words, just give not all the topics at once, but a certain set of them. So today I'm going to cover these 3. So we're going to cover systems, the gravitational field, and contact forces. All right. So the first thing that we're going to look at are systems. Now this is interesting because you could have a lot of different types of systems. So I'm only going to cover 2. Most likely you're going to see some form or another of these systems on the exam. So the first one, and we have done this, or you should have done this in your AP class. The first one is going to be an inclined plane. So we're just going to have a ramp, all right? And then as you know, we could move this ramp into different locations. So let's just draw 3 of them, all right? So the first one is flat like this. The second one, we're going to create an incline. So we're going to have some sort of books or something to keep that there. And then we'll just make a third one just to reference that. And we're going to draw this one like this. And what we're going to say here is that this angle here, so let's call this angle 1, is greater than this angle here, which is 2. So angle 1 is greater than angle 2. I'm going to try to keep my handwriting neat so you can see this, all right? So in the system, if you remember the experiment that we could run with this is putting a ball, okay? So if we put a ball, or we used a marble on here. So if you have a marble and you think about what's going to happen in here, that marble would stay still on the level surface. But as soon as you had an incline, unless you had a ramp that was made out of tar or had some sort of glue or something on there, we would imagine that that ball would always roll down the ramp. All right? So in this system, because we have the ball, then we can assume certain things. So let's say that it does roll down. First of all, when it rolls down, it's always going to be speeding up. All right? And what's going to happen to that speed if we increase the angle there? Well, it's going to go faster. All right? So in these systems, what they're going to ask you is what happens if I change something else. Now, the advantage of doing experiments with this is that the experiments will let you have a hands-on approach to it, and you'll be able to identify what's going on and think about what's happening. But realistically, guys, if you just been able to look at certain things, the way the world works, or just different experiments and stuff, then you should be able to come up with some of this stuff. And that's what they're looking for in the AP exam. Not necessarily that you've done all the experiments that are possible, but they want to know what would happen if we did something in this system. Now, there's one thing that we haven't drawn, and I'm going to say the Earth. Out of everything we do, the Earth's always going to be part of the system. And I'm going to introduce the first thing here. And the Earth exerts a force, and we call that gravity. Force due to gravity. All right. There's another term to this, and this is the first one that we learned. It's also called weight. Now in the AP exam, sometimes they say W for this, but I always like to say force gravity because I label all my forces the same way. All right. So the Earth is always part of this because what would happen if we didn't have gravity here? Then that ball is moving downwards because of that force gravity. So force gravity is always part of that system. So this basically covers our first system, which is an inclined plane. The second system that we're going to talk about is the Atwood machine. The Atwood machine is definitely used on the AP exam because there's almost an infinite amount of possibilities that you could make with this. But basically what we have is we have the pulley, and then we have a string over the pulley, and then we have two masses on here. So this is our first example of an Atwood machine. Now I'm going to label this A, and I'm going to label this one B. Now if we don't include the effect of the pulley, in other words, we neglect it. However, if they ask for rotation, you could actually put it in. Then we can consider this a system between A and B. So what happens if A is greater than B? Then we know that this is going to move in this direction. It's going to speed up in that direction. What's going to happen if A is less than B? It's going to speed up in this direction. And what's going to happen if A is equal to B? Then that system is going to be in equilibrium. It's not going to move at all. And once again, what's causing this movement? It would once again be force due to gravity. Now the other Atwood machine that's often seen is the one that looks like this on some sort of tabletop. So you'd have some sort of object here, and then you'd have some sort of object here. So if we call this one A and B, what can we say about, let's say A is greater than B in this case. What would happen to this system? Well, we have to include another force here, force friction. So does the table have friction or not? In a realistic situation, it would always have friction. But let's just start out at a basic level. Let's say that there's no friction. If A is greater than B, we would still have movement in this direction. Because in this situation, we won't consider any friction. Force gravity is always going to pull down in this direction here, right? So we don't have a situation where this will ever move over here unless some force is being applied to move it in that direction, okay? So if A is greater than B and there's no friction, it would definitely move up in that direction and it would speed up. However, if we added friction there, you could see a situation where A is greater than B and it doesn't move, all right? You could see a situation where we add some mass onto this and then we figure out what happens. Let's call this C. We figure out what happens there. In this, you can't automatically assume that something is going to happen because you would have to do the calculations. So this is the one that they like to always include on the AP exam. They also like to add springs here. They like to add projectile motion. They want to see what happens if we add something to here. This is like the perfect example of a system where you have to think about what's going on. So this one's the most common system, all right? So that covers what type of things that you may see as far as dynamics. You're either going to see some sort of inclined plane and an Atwood machine, or you could see a combination of both. Now, I didn't go over any of the math or anything. I just wanted you to give you a familiarity or an idea of these systems to get you just thinking about them, right? Okay, let's go back to the second part of this. Gravitational field, we just talked about that, and contact forces. All right, so force due to gravity, which is also called weight. Now, there's a formula for this. It's mass times the acceleration due to gravity. So it's mass times gravity. And remember, mass, so let's just start going into units. Mass is in kilograms, and gravity is an acceleration, so it's going to be meters per second squared. All right, now there's a lot about gravity that we don't discuss in physics, so we just do it as a vector. So let's define what a vector is. A vector has direction and it has magnitude. Now, how do we represent vectors? We represent them by arrows. So this would be a vector, and this would also be a vector. What will be the difference between the two? This one is simply larger than the other one because it's longer. That's what we mean by magnitude. What else could we say about magnitude? So if this was, let's just say this is a force. So let's say this was 5 newtons. This one would be greater than that, 10 newtons. All right. Obviously, you can have different directions. So you could have east, west, south, and north. These can also be considered left and right also, right? And then you can have diagonal vectors. All right, so as far as forces in general, you could have these different directions. But force gravity is nice because force gravity always goes straight down. And if we're talking about the Earth, then it would be the mass times 9.81 meters per second squared, because that is the acceleration due to gravity on the Earth. Now, remember that this has to be in kilograms. So kilogram times acceleration, that gives us our unit of newtons. Now, all forces are in newtons, and I see a lot of mistakes with force gravity. Sometimes they'll put 9.81, but that's the acceleration due to gravity. Sometimes they won't convert mass into kilograms, so just make sure you're doing that type of thing. All right. So that covers that, and that leads us right into our contact forces, which means that force gravity is called a field force. So field force means that it acts at a distance. It doesn't have to have direct contact. And that makes sense because if you're in the air, force gravity still affects you. If you're on the ground, it still affects you. It doesn't matter whether, like, if you're in a building, this is the one I like to use. If you're in a building, right, and you have floors there and you're on the top floor, force gravity still affects you. If you're on the second floor or the first floor, whatever you want to call it here, if you're on this floor, force gravity still affects you because it goes through it. That's why it's called a field force. There are other field forces, electrostatic, magnetic, but I don't think we'll be discussing those. All right. So the other type of force is direct contact. And for these, so let's put force gravity as our first one. I also mentioned another one, force friction. Now I'm going to call it force of friction. Okay. FFR. It can also be called different terms, but whatever way you learned it, you know that that's force friction. What's another one? Applied force covers a push, a pull, anything where an engine, anything could be under this applied force. What's another type of force? Force tension is also very common. Force tension is when there's a rope or a string along that force. Okay. Tension can also sometimes be abbreviated by T, just like force gravity was weight. Let's see, what else do we have? We have buoyant force, we have electric force, we have applied. We have a force applied by a normal, which is Fn. This one often confuses people. You need to have a surface in order to create a normal force. In other words, if a ball is falling through the air, it does not have a normal force. So this leads us right into our free body diagram. Now, free body diagrams are where you should almost always start, all right? And I think the confusion with free body diagrams is if you have more than one object. But remember, a free body diagram just covers the forces on a single object. So even if you have 3 objects in a row, you would have 3 separate free body diagrams representing the forces on each of the objects. So let's start out real simple. Let's start out with a ball falling to the earth. Now, if we neglected air resistance, we would only have one force, and you can always draw this one first. It is always force gravity going straight down. Now, what happens if we have air resistance? Well, then we need a force that opposes that. We would put force, I'm just going to put air resistance, AR. But we could also call that force of friction because air resistance creates friction. All right, so that's a ball that's moving in the air. Now, what happens if we have a ball on a surface? So let's put that ball on a surface. We once again draw force gravity. But since it's on a surface, what are we going to do? Force normal. Do you notice how the other one didn't have force normal? Because it's not on a surface. So the normal force is created by the surface and the interaction with the object. All right. Now let's cover our 2 examples here. Let's cover our systems. All right. So this is our inclined plane. And I'm going to put some sort of an angle here. And then I'm going to put a box on this inclined plane. Now, what forces would it have? It would have force gravity going down like this, and then it'd have a normal force like that. All right. Now, if you notice, the normal force must always be perpendicular to the surface. So let's add that over here. The normal force must be perpendicular to the surface, which reinforces the idea that it's the surface that causes that normal force. All right. Let's look at our Atwood machine here. So the first one, we had a rope and we had 2 masses. So this would be A and this would be B. Both of them have force gravity, and I'm going to put A for this one and I'm going to put force gravity B for this one because they could be different if the masses were different. All right. And then I'm going to include a force tension because it's through a rope, force tension A, and I'm going to include force tension B. And finally, one more system with this, and that was the Atwood machine that looks like this. So we have a pulley, and we have a mass, so I'm going to call this mass A and mass B. So let's draw the surface, the forces on this. This would be force gravity A, and this would be force gravity B. Oh, sorry, this one's A, and then this one is B. And then what do we have here? We have a rope here, so we have force tension of B. And then this is definitely on a surface, so we have normal force. Now, what else do we have here? We definitely have force tension going in this direction, force tension A. And then let's just say there was friction on this table. So friction always, well, not always, but in this case it would oppose the motion. So this would be force of friction. All right, I think we used all the forces except an applied force. So let's just draw a diagram for an applied force just so we see all the forces. So let's draw a car. This is the way I like to draw my car. And we're on a road. So what do we have? We have force gravity. And since it's on a road, we have a normal force. And we're going to say that it's moving in this direction. So we're going to say some applied force is moving you there. Force applied. I like to be specific sometimes, so I could say force of the engine. So in this case, the force of the engine is the applied force. And just in a normal situation, we would definitely have force friction. And that would be our free body diagram for it. All right. So force friction is definitely a contact force. Applied force, a push or pull, contact force. A rope, contact force. Normal would be a contact force. And force gravity would be our field force. All right. So we've covered different free body diagrams. I'm hoping that everyone's comfortable drawing free body diagrams. The only thing we didn't really cover was a force at an angle, but we'll get into that when we start looking at calculations. All right, let's revisit the previous inclined plane and change our ball. So I'm just going to erase all this. Alright, so let's redraw this inclined plane. So we have an angle here. And this time we're going to change it into a box. Now in this case, without any other data, we would know that this box would either stand still, so that would mean that the friction on it, on the ramp, was great enough that to keep that box on the ramp. It would speed up going down. And I'll just put down the ramp like this. Alright. And then what's another condition that could happen? What happens if the box was already moving? This is interesting, because if the box was already moving, then it could actually slow down going down the ramp. Alright. So as far as the system, our three different concepts would be standing still if the friction was great enough, speeding up down the ramp, or if it was already moving, it could slow down the ramp. And there's no condition where this would ever be going up the ramp. It's not possible in this situation, all right? Because gravity is just going to pull it down. However, and this is an experiment that I usually do, we could also attach something in this direction to make an Atwood machine, right? And look what we have. So we have an inclined plane with an Atwood machine. So let's label this one A, and then let's label this one B. And while we're at it, let's just make the free body diagram for this. And I'm gonna use a different color. Let's use blue. Okay. So the first one would be force gravity on B, and then we would have force tension on B. Then we would have force gravity A, and then we would have force normal of A. And then through the string we would have force tension on, oh sorry, that should be an A. Now let's take a look at this, because we're going to once again assume that the pulley doesn't influence the system at all. And if we had a force friction, our force friction could actually go in two different directions depending on what was happening. Let's say that they were in equilibrium. If they were in equilibrium, that would mean our force friction would be right there, because that's the force that's balancing that out. All right. Now let's say it was speeding up. A was speeding up the ramp. If we had friction, friction would also be in the same place. But let's erase this. let's erase that and say, and I'm going to make this one red just so that you can see it differently. Let's say that the A was moving down the ramp like this, which is completely plausible, all right? If A was larger, it could pull B, which is smaller, up the ramp. It could pull B up and then A going down the ramp. In this case, our force friction would actually oppose the motion. So force friction would actually be right there. So it switches sides depending on what's happening to the system. Now you can see how we took this inclined plane and now we added a box to it, and there's a whole bunch of other things that can happen to the system. You have to be able to think about all these, and I wouldn't say memorizing, but intuitively through the concepts. And that's what makes physics difficult, because there's a lot of different things that they could ask. All right, that wraps up the systems. All right, guys, systems. We covered inclined plane, and we covered Atwood machine, the gravitational field, which is a field force, and we labeled that as weight, and it's mass times gravity. Oh, just to mention, remember that mass will always be the same for the same object. So it doesn't matter where that is, but your weight can change depending on gravity, which explains why a person on the Earth would have the same mass as that same person on the moon. But since the gravitational field around the moon is less, then the weight would be less, not the mass. And then we covered our contact forces and free body diagrams. All right, I think that covers this video. It's good about videos. You can go back and look at the stuff, and hopefully that gives you a better understanding of the basics so that we can continue on with the first and third law in the next video.